Hello and welcome to our newest episode of the CATIA Design Talks. My name is Honorata Frinks and our topic today is once again the beautiful Aurora installation that we already introduced in October to you. This time, this broadcast is pre-recorded due to some time constraints that we had. So if you want to ask questions to our expert, please do this in our community. You see the link below. And join the community at any time. You can also place the questions right away here. Let's start. This art piece was created first by Mamou-Mani architects and Dassault Systèmes, and it was part of the Waste Age exhibition in London last October. As we already introduced this project in our CATIA Design Talk in October, we will pick up one specific topic today, parametric design. To give you a deep insight how the X-generative part was done, I have invited Nicolas Cinnamon with me today. Nicolas is a senior solution architect at Dassault Systèmes, specialized in complex geometry, parametric modeling, and data management applied to AEC. Before we welcome Nicolas, let me give you a short overview about Aurora.
I'm Arthur Mamou-Mani. I'm an architect and a teacher based in London. At Mamou-Mani, we work with parametric design and machines and try to unite all this into a system to learn about materials and create sustainable design based on natural processes. We're both designers and also the fabricators of our projects. We have Mamou-Mani, which is our architecture studio, and downstairs we have our fabrication space. Having a prototyping facility downstairs allows us to set up an empirical loop in which we can constantly iterate and fail and learn. It's really an integral part of innovating and creating new things from failure. We're collaborating with Dassault Systèmes on an experimental research project that will end up as an installation, which will describe the life cycle of materials and apply technology to understand the science behind it. Dassault Systèmes have an online platform, 3D Experience, which is a suite of apps for designers, and they were curious to understand our workflow. They're developing a parametric tool called XGen. It allows to create parametric models within the Dassault Systèmes suite. The installation is made of a dynamic grid of 3D printed modules, then cascades through that space as if it was taken by the wind. As part of the installation, we'll have a 3D printer on site that will be printing modules in bioplastic PLA made from fermented sugar. When the PLA comes, it comes in pellets, and then we print it into objects. The material that we used, it's renewable. It comes from renewable sources that are sustainable, contrary to petroleum-based plastic. The advantage of building with 3D printing for architecture is that you can print on site. It's also much more efficient because it's directly linked to your computer models. There will also be a plastic crusher on site, showing people how recycling can be done on a small scale. The plastic crusher allows us to take a piece that's already printed and bring it back into the pellet form that allows to print again. From 3D printing to crushing to composting, we wanted to show all the states of the material that is ultimately a renewable, cradle-to-cradle and sustainable life cycle. Dassault Systèmes had this really wonderful tool that allowed us to put science and metrics behind life cycle assessments. It allowed us to compare different materials, different approach, and all the different advantages and disadvantages of each. It's very important that designers start thinking beyond the time frame of their project. They need to start thinking of where the material came from, where is it going, how can it be reconfigured. The entire life cycle of this project needs to be taken into consideration.
Now that we have a little overview about the project as such, I would like to welcome Nicolas.
Yep. Hello everyone. Hello, Narata. Thanks for inviting me.
Great to have you. Actually, I love this piece of art, and it's a pity that I was not able to see it live. So it's really beautiful, and it's quite complex. And as a matter of fact, it was not planned to be installed in the Design Museum in London in the first place. It was built for Milano. What happened, and how did you achieve it, to build it, set it up in London instead?
Yeah, so basically what happened is that I think it was in September 2019 we basically started brainstorming with Arthur Mamou-Mani and the design studio to create a piece of art that would raise awareness around questions on sustainability, eco design, new materials. And so pretty quickly we started like brainstorming on the community that is actually on my screen here. So this community was basically the place where we would exchange ideas. We would post pictures of materials. Arthur would share other references. So the main concept was actually designed on this platform. And you're actually totally right. The piece, the installation, was meant to be put in inside the Super Studio Pew exhibition room, which is actually this one. We're gonna see an image. So I'm gonna show a bigger model of it, but like this is an extract from the preliminary studies from Arthur Mamou-Mani, and you can obviously see the space. So it's not very high. But it's pretty wide. It's pretty wide and long. So the footprint
Much
of the art
bigger.
piece
Yeah.
was much bigger. But here you can see that since the very beginning, Arthur had this idea of creating a sort of wavy, flowing structure like this, like an Aurora. It was basically meant to be an immersive experience, but composed by modules. And as you can see, in the very early studies of Arthur Mamou-Mani, he was already studying how many pieces, how many modules could fit into one footprint of the printer. So this was it was like it's completely disruptive as a design process. Is that Arthur as a maker was thinking about the module itself and how we would construct the generative system to generate the installation. So the end installation wasn't an end of, I would say the installation, sorry, wasn't an end in itself. It was more about the unit, the module, how it was going to be made, and the generative system that would define basically how it was going to be assembled. So pretty quickly we started testing, and as you saw in the video, it's very important for Archer to have like this trial and error process, which is
Yeah.
absolutely essential in all design processes. But he started doing physical models, and as you can see here, like he was already defining, I would say, the underlying rule behind the whole installation. So we actually used generative design, which I'm gonna get a bit. We're gonna deep dive in it, but we used generative design to model behaviors. We weren't model 3D. We're just modeling behaviors to basically try to mimic and to converge to a system actually that would represent, embody the questions that we want to ask to our, for this project. So that's just a video, that shows the very first draft, showing how we could play with the angled aviation, with the length of the
Mhm.
modules on their general layout inside the design museum. So all this was driven by, again, parameters and the modular approach. So we would be able to generate lots of different options in order to basically do, I would say, an actual proposal. But the concept of it was always centered around the module. So that's just an example, but
So
you can.
actually, originally it was planned that you can pass through the model. So it looked like there was a path between the modules,
Exactly.
and you have this hanging modules above. right?
Yes, exactly. So,
Can you
so
explain?
at the very first, we didn't know if if some modules would be hanged or suspended, or all the modules would be lying on the floor. But you're right. Like we converged pretty quickly to a solution where we would have modules lying on the floors and modules hanged at the ceiling. So a little bit like this. So this was, I would say, the one of the last iterations. So here you could see that we sort of mirrored the installation from bottom to top. But and after when we refined the design, we reached, I would say, a state that would be a bit more like the one I have on my screen here, which is basically a sort of um, installation that would elevate itself, that would just take off from the ground to the air.
By itself.
Yeah, exactly, and the visitor would could go through it, from a path that's like this. So yeah, as coming back to your original question, it was meant to be designed ad hoc inside the I would say the Super Studio Pew space. It was very specific to it. But at the end, as I was saying, we didn't really model this installation piece by piece. We modeled the generative system that would basically colonize any given
Right.
space. So at the end, if the generative system is consistent enough, if it makes sense, if it's robust enough, then you can make adjustment, you can change parameter, you can transpose modules one with the other, and at the end it doesn't really matter where it is. It does have an impact on the code behind it. If you want, we can have a look to the actual parametric model, so we can
Yes,
understand
that
the
that will be great.
adaptivity.
Absolutely. So what happened, just for the info to our audience, of course, COVID happened, and we had to cancel the event that this installation was originally built for. And it took a year, so it was a year break until we found that now it's time to do this installation, but the event was gone. So we searched for another place to set up and display Aurora. And then we found this one in the Design Museum in London. And then all the setting had to be changed. And Nicolas, you can explain to us how you did it.
Sure. So here I'm actually showing on the screen the design museum. So how it is. So here you can see that the space is totally different. It's not wide. It's actually pretty narrow, but very high. So it's we had the opportunity to display the installation in this atrium that is going through 3 levels. It's a wonderful space. It's really amazing, but it was quite different. So I can actually show the end result, which is
Yeah.
here. So you can recognize you can recognize the piece, right? You can understand that it's made of the same module. Yeah, the stacking system is the same. Hanging structure is also kind of the same. So you can recognize it, but it's true that it had to adapt to a new environment. It's much narrower, the space we were fitting in. There is no module lying on the floor. We had quite a lot of security requirements, like the height clearance, for example, so that people couldn't touch directly the module. They could touch it, but like not on the ground floor. But so new requirements. And also what's really important to notice that um, when we designed this piece in Milano, we went very far in the design process. Arthur Mamou-Mani already printed all the modules, most of it. And here, when we had to transpose the piece the design museum, like we had to reverse engineer a bit. Like it wasn't the model that was defining the number of modules. We already had the number of modules in the storage room, so we had to basically add these new requirements to the generative system, so it could generate exactly the number of modules that we actually had. So actually, I can basically go inside the XGen model,
Yes,
so that
please.
maybe we can understand how it adapts, right?
Yeah, that would be
Um,
great.
so basically, XGenerative design was basically the cornerstone of this project, because XGen creates basically what we could call the parametric skeleton of the virtual twin of this installation. So it's a computational tool that allows you to create design rules, that allows you to constrain geometry to give it exactly the behavior that you actually want it to have. It has a visual coding interface that allows you to code it entirely. So that it's entirely adaptive, it's entirely parametric, and you can create quite complex behaviors behind it. So it's very sequential. So here, if you see on my screen, you know, like you read it from left to right. So the inputs are on the left and the outputs are on the right, and everything between is process. So in blue, I'm basically processing my inputs. We're gonna see what are my inputs. In green, I'm defining the 2D pattern. In orange, I'm defining the 3D geometry of the module itself, and in red, here you can see that I'm basically extracting from the skeleton what I actually need.
Does
So
it mean that when you change any of these parameters, and then it will be all recalculated and assigned back to a working model?
yes, exactly. So here I have exposed parameters, I have hidden parameters, but the radii of the module is driven by the step, sorry, of the grid. Length of the step is driven by parameters. The height, pretty much everything except one thing, which is related to our main question. Here you can see that the modules are basically, you know, they're colonizing a given space, and you can see this shape here that is pretty clear. And this shape is defined by two surfaces. You have a top surface here, and you have a bottom surface here. Let me see if I can actually show it, because it's I think it can be pretty handy. Actually, it's this one. Yeah. Oops, let me hide this. So here, oh no, it's sorry, it's not this one. Yeah, it's this one here. Yeah, perfect. So here you can see the two surfaces, and actually those are the only two inputs I actually need. Is that I know I have a top surface, I have a bottom surface, and those are imaginary shaped surfaces. So you just need to push and pull the points to adapt the installation to a given space. So this is basically what happened when we transposed the Milano install to the London installation, because we just took the surfaces, we lifted up, we pushed and pulled the points, and then after we trickled a bit the code so it would match exactly the number of modules. But here it was at the end. It's the actual generative system that defines everything, and everything starts from only two surfaces. So if we had to recreate it elsewhere, then you would just need those two surfaces to recreate exactly the same behavior, and so on
So
and
you
so
mean by
forth.
the surfaces is the surface or the heights that you have in start and end of the structure, right?
Yeah,
Okay.
yeah.
That's
So,
pretty cool, actually.
yeah. So let me maybe show you really quick the how it's the different outputs I have on the script. So here, for example, in that part, as I was saying, the green parts are defining the 2D grid. So here you can see how you can see the field of vectors that we created to basically give to the module the actual orientation. So so to define this field of vectors, it was a mix between the actual curvature of the surface, but also a bit of randomness, but not that much. And then what we did after that is that we actually just um, populate. Yeah, we basically populated the whole space with those vectors. As you can see here, we translated them by the height of each module, and what happened is that we created all the we populated the whole bounding box of the surface with of both surfaces with those modules. So here you can see that the modules are stacked in staggered rows, so that it would ensure structure stability. But overall, the structure is pretty much the same because the levels are the same, but again, to ensure stability. And after, basically, you just filter out the modules that are inside the surface, and then after you basically segregate them into different module types. So here, if I come back to the 3D, let me just hide the surfaces here. And so coming back to the graph, after, you can basically segregate those different modules exactly as you want, based on whatever rule you want to put. But most important of all is the output of XGen, and that's really disruptive in a way of doing computational design. Is that we were using a computational design tool not to generate very complex geometry. We were actually using computational design tool XGen in that case to generate the 3D specification of the skeleton of the virtual twin. So here, the only output I actually have are planes, to which define the position of the actual real module, which again I can show here. So basically, we had a library of different modules. So we had module type A, B, A1, B2, whatever. And what we did is that we basically linked those PLM objects to the position that we were specifying in XGenerative design. And with the simplest trick in CATIA, using an assembly pattern, I have a quick video of that. We were able to, in a couple of clicks, to generate an LOD 400 virtual twin of the installation that was going to be used for renderings, for life cycle assessment, for structural analysis, for assembly simulation, and all of this was relying on the parametric model.
That would be interesting to see if you can show us the video. How it's
yeah, sure. It's actually this one. So here, sorry for the low quality of the video, but I'm sure we can still understand what's going on. So as I was saying, this is the XGenerative design skeleton. We're only interested into the axis system that are published to reposition the detailed modules. And just by the way, those modules are the same modules used for manufacturing. So the G code generated for the printing come from the same modules. So you have a continuity between, again, manufacturing and design in that case.
Yeah, so that is something we really need to point out, that this is extraordinary. So there is no jumping back and forward to different software solutions, or you just remain everywhere all the time in one platform, and you can work collaboratively on that and get your results ASAP.
And yeah, having the model very consistent. So for example, we didn't duplicate the rendering model from the manufacturing model or the manufacturing model from the parametric model. Everything was totally centered on one piece of model, on one model, and what is absolutely essential, even more when you have such small time frames to design. So, sorry, coming back a bit on the video. So here, basically, I placed the module on an access system, and it's called an engineering constraint. Simplest trick in CATIA, it's done in a couple of clicks. And because the generative system is dependent on the size of the module, you're sure it's going to fit. You're sure the module is going to fit exactly the position that has been defined by XGen. And here, when you have defined this engineering connection, in a couple of clicks, you can replicate the same constraint to the list of the access system, and here, it's done. Like here, you have created different instances of the same reference. It's a super lightweight model, but it's very, very detailed, actually. So at the end, as I was saying, you end up having the virtual twin of your installation. And again, coming back on CATIA, I just wanted to show a bit the structure of the data model behind it. So you have the master model, the root. You have here the environment, and here this is the skeleton of the installation. But all the modules are outside the skeleton, and that's very interesting, because it means that you dissociate the parametric skeleton from its actual detailed parts, which means that you are able to still be very agile and flexible. It's still designing the parametric model without having to load all the other geometries, or without having any clashes with the other components that you already instantiated. Those are totally dissociated, but still connected. So if you make a change on the parametric skeleton, then it's the whole virtual twin that updates. You don't need to redo all the steps again and again. So this is for me absolutely key, being able to do this dissociation, because you stay very agile on the parametric modeling side of things. And actually, I have the Design Museum version open here. And yeah, this way, what we would be also able to share the model much easier with the different stakeholders, for the people who did the renderings, people who did the structural analysis. And what was really awesome, actually, is being able to work on the same model. So this model. With Arthur Mamou-Mani's team. So this is visual programming. This language exists for a decade now, but we integrated into the platform, and we were able to exchange much more easily with Arthur, because they speak also this language very, very well. And with the time difference, I would, based in Canada, I would make a change in the model. I would update Arthur Mamou-Mani. They would open on the same dashboard the model. They would see the modification. They would make corrections and modification, and so on and so forth. But it was like everybody spoke exactly the same language, and on the same platform. So it was actually a great example of collaborative work.
Yeah, absolutely. I think that is a key takeaway here for sure, that you can work collaboratively at any time from anywhere. Even, I don't know, probably you worked on the cloud as well for this project.
Yeah, exactly. Yeah.
So everything is on the cloud. You don't have to install anything at all. And that's it. You start, you do your parametrics, and you're good to go. And this is quite impressive that you are so flexible. So you don't have to redo all the designs. You can just take parts of it depending on how you set up the design. You are as flexible as you want to be, right?
Exactly. And I would just like to add also that at the end, obviously we use computational design technologies, but in a very disruptive way. And I would say that in normal kind of modeling process, especially in design and in construction, we tend to do everything in one software. And here it's totally different. We use different bricks. We use XGen to do the algorithmic design. We use assembly design to do the assembly pattern and constraints that we saw previously. We used live renderings to do the renderings, life cycle assessment to do life cycle assessment, and the community to collaborate, whatever. So it's like basically it's like taking the best of those bricks, and because they're connected and because everything is unified with one data model, we were able to have, as I was saying, the best of every of those bricks of technologies to do renderings, detailed modeling, whatever. But still, what's interesting is that the computational technology still stayed at the cornerstone of the whole process, and that's very, very disruptive compared to normal processes where everything tends to rely on one big modeling tool. So so yeah, I was really happy actually to push this project until the end, but at the end, you know, the real I would say that the real output, the real trophy that we of this project is in the real world, right? So it's actually when you enter a design museum and you actually see the piece that you've seen for so many months behind your screen being built up, that it's actually breathtaking. It's
and it looks so light. It is. I think it very much matches the colors of the design museum entrance, and it appears to be so light. You know, it's light in weight and light in color, actually.
It was a beautiful, beautiful piece.
Beautiful, yeah. You can, if you want to, so to our audience, if you want to find out more about Aurora, you can also visit our design portal. We can have the link in the banner maybe in a bit. There you have all the aspects of the whole Aurora installation that you can see and discover even more. Yes, there, and just give me a sec. And this one. So visit 3ds.com to visit our design portal of Dassault System. Here you will discover not only Aurora, but also other projects that we are working on. But we have this live Aurora that you can visit and discover in all its facets. Yeah. That's it, I think. Nicola, it was a great pleasure, because for me it was the first time to see how this whole project was set up and built, and it's really something different when you get a whole overview. And I really usually like our solutions in work when you can see how easy you can get your design, you can set it up, and you can do changes. And of course, you can collaborate. So that's a key benefit of it all.
No, yeah, sure.
Yeah.
My pleasure.
Thank you. So as I said, this is not a live broadcast this time. This is a recording. So this time, if you have any questions to Nicola, please visit our community and join us here. We will happily answer all your questions. And that leaves me with a thank you and goodbye. See you next time. Bye-bye.